students, welcome to the channel Physics by Dr. Pradnya, and today we are going to see very interesting topic which is known as nuclear forces. Okay, so let us see what are these nuclear forces. So the nuclear forces are the forces which are present inside the nucleus, or the nuclear force holds the nucleons together. So we know that in a nucleus protons and neutrons are there, and these protons and neutrons are bound strongly with each other with the help of these nuclear forces. So today we are going to see what are the properties and what is the nature of these nuclear forces. So let me first tell you that in a universe there are four types of forces are there. So according to the strength, okay, so the weakest force which is present, which is a gravitational force field, okay, then electromagnetic force field which is greater than that, then weak nuclear force and a strong nuclear force in a order of the increasing strength. So let me write this four forces. So first one is gravitational. So let me tell you that if I assume the strength of the gravitational force field as 1 unit, then it is 10 raised to 36 times stronger than this gravitational force field. So you can imagine the strength of the nuclear force. Okay, so we can say that the nuclear force is the strongest force in the universe. So let me write here. So nuclear force is a strong force. Now let us see what is the range of this nuclear force. Means up to what distance the two nucleons can attract each other, or at up to what distance they can bind or hold together. Okay, so if you see the gravitational force field, its range is infinite. Okay, that's why the sun and the earth, the sun and the Pluto, they are also still bound with each other. So we can say that this range is infinite. But when you speak about the nuclear force, they are uh, present, or they are active only in a range of the femtometers. Okay, when we are dealing with the nuclear and particle physics, we speak in the distances of the units of the femtometers, which is 10 to minus 15 meters, which we have already seen in our previous lectures. Okay, so this nuclear force, it is present up to only some distances. For example, if I try to draw a diagram of this potential energy or the strength of the interaction versus the distance r. So if suppose I have a proton over here and some another nucleon, like another proton or another neutron is coming from this side. Okay, so there will be force of attraction between the proton and neutron. So let me draw here a neutron. So they will start interacting only if the distance between the proton and neutron is less than 2 femtometer. Okay, if this r is less than 2 femtometer, 2 to 2.1 femtometer. So if the distance between the proton and neutron is less than 2 femtometer, then only there will be the attractive force between the proton and the neutron. Okay, so this diagram, so let me draw it like this. So see here, so in this range, so this R naught, we can say that if this R naught distance is 2 femtometer, if this neutron comes closer less than this 2 femtometer, then and then there will be the interaction between the neutron and the proton. Okay, and when we know that whenever there is a bound state is formed, so some stable state is formed and the energy is lowered. Okay, so the total energy is shown in a negative direction. Okay, and if I supply the same amount of energy, again the neutron and proton will separate out. That's why we are showing it at a negative side. Okay, now see here. So this distance, again, if this neutron is reaching towards this proton at a distance less than 0.5 femtometer. Now see here, if this r is less than 0.5 femtometer, okay, there will be the force of repulsion. See here. So when this neutron reaches the proton at a distance less than 0.5 femtometer, there will be a repulsion between the two nuclei. It means that the nuclear force show the attractive nature if the distance between the two nucleons is in the range of 0.5 femtometer to the 2 femtometer, and they become repulsive for the distances less than 0.5 femtometer. This is why we can see that if there is a nucleus and these are the nucleons inside it, classical mechanical picture, and suppose these are the protons and neutrons will be there in the nucleus. So for this proton it is not possible to attract this proton because it is at a distance greater than 2 femtometer. Therefore we say that the nuclear forces are short range forces. See here, short range forces. So the another property of the nuclear forces is they are short range. They are present for a very shorter distance. Okay, so the distance is in a femtometers and the range of the attractive force is 0.5 femtometer to the 2 femtometer. Okay, big energy which holds these nucleons together, it is directly proportional to the A and not A square. That's why each proton cannot attract each and every proton or neutron inside the nucleus. Therefore, the binding energy is directly proportional to A and not A square. Okay. So this is how the nature of the nuclear force is. It is a short range force. We already came to know that it is the strongest force in the universe, and it is also a short range. Let me tell you about the strength of the interaction between the two neutrons, two protons, or a neutron and proton is same. We can say that these are the charge independent forces. For example, the strength of the interaction between the two protons, two neutrons, or a neutron and a proton is same. So we can say that, and we know that this proton and the neutron have a different charges. So we can say that these nuclear forces are charge symmetric, okay, or a charge independent forces. The strength of the interaction between the two protons, two neutrons, and a neutron and proton is the same. So this is all about the nuclear forces. Thank you for watching.